Hello and welcome to lesson 34. Today we are looking at regular annuities. We're looking at present and future value for these annuities. And our learning goal today is to be able to define what an annuity is, determine the effects of the change of changing the conditions, such as different payments, the frequency of the payments, interest rate, compounding periods of simple annuities. So, our key vocabulary today. First, what is an annuity? So it is a series of equal payments that are made at regular intervals. So consider you're investing for your future and you want to start a savings account and you want to deposit money to the savings account each month. That would be an annuity. And so we can also calculate the future value of an annuity, which means that the total value of all the payments after the last payment is made, and also with consideration to the interest that is added. We can also consider the present value, which is the value today of the annuities that, or all the future payments that you're going to make. So how much money is there right now? Because this could also be it is, yes, you are investing, but it could also be that you are also depositing money. So how much money needs to be in that, or sorry, withdrawing money. So how much money needs to be in that account right now for you to be able to have regular withdrawals at a regular interval as well, which we will see an example for that today. And payments are the fixed deposit or withdrawal each period. And thinking of our interest, periods can be different as well. In this case, we can do monthly, yearly, and so on. We also do have two types of annuities. We have ordinary or simple annuity, which is when payments are due at the end of the period, and annuity due when payments are due at the beginning of the period. So consider, for example, if you're doing monthly payments, in ordinary annuity, the payments are made at the end of the month, whereas in annuity due, the payments are at the beginning of the month. So we are really only looking at ordinary annuities, or again, simple annuities where the payments are made at the end of the period. And we have our two formulas here. Again, it is the same formula, just rearranged. So don't worry about having to memorize two formulas. It's only one formula that you really need to know and be able to use because the other one is simply derived, can be derived from the other one. So in this case, for future value, so you are perhaps depositing money and you want to save up for the future and you want to know the future value. So the future value will be given by R, which is the payments that are made at the end of each period. And then we have 1 plus I, which I is our interest rate per period. Again, remember, any interest rate that's given to you is per annum, so we need to calculate per period, do the division depending on what that period is. And n raised to the power of n, which is the number of periods. And think of that if it's monthly and it's 2 years, n will be 24. And then we subtract 1 and we divide by that I again, the same I value there. Now, to find the present value, so this is especially useful, for example, with retirement or, for example, a big saving goal that you have. You want to save up for a certain amount and you want to know how much money do I need to invest in this account right now for me to be earning interest on this and to have a final future value that is desired. So the present value will be given by, again, R is that regular payment. Now we have, instead of the bracket minus 1, we have 1 minus the bracket. And now it's, the power is negative n. And again, we divide by I. So all of those variables are the same in both formulas. It's just the rearrangement of them. So please familiarize yourself with these, and we will see throughout our examples in this lesson how to use them. So let's get started with our first example. Suppose you deposit $40 into a bank account on New Year's Day. You continue to put $40 into the account on the first of every month for the rest of the year. The bank account earns 6% interest per year paid monthly into the account at the end of each month. How much money will be in the account at the end of each year? So in this case, it is a little bit different the sense that we are depositing at the beginning of the month, but then we're earning the interest at the end of the month. So that's why we have the table set up. So on January, so on New Year's Day, we had deposited $40. At the end of the month, we earn an interest rate, and it is 6% per year, which means that to calculate I in this case will be 6% divided by 12 because it's monthly, which will be 0.005. So on that $40 that I invested at the beginning of the month, which is also here my balance, then I earned 0.005 or 5%, 0.5% of that $40, which was 20 cents. So at the end of the month, my balance is $40.20. Now I'm going to do maybe a couple more rows and then let you try the rest. So now February comes around, and again, on the first of the month, we make a $40 deposit. But we already had $40.20, which means my balance at the beginning of the month is now $80.20. Now I earn that same interest, but now on $80.20. And so I would get, oh, and only keep two decimal points because we're working with money, so it'll be 40 cents there or 0.4. And now my balance at the end of the month with that added, and remember, we go now from the balance at the beginning of the month, which was $80.20, and now we have 40 cents added. So, and I don't need to put the dollar sign because I already have the dollars in my title there. So here, $80.60. Now, again, in the next month, March, you deposit $40 and you already had $80.60. So now your balance is $120.60. And now we have 0.5% interest on this, which will give you 0.6, or maybe let me write it out for just this row as well. This will be 0.60. And now, adding this onto the $120.60, we have $121.20. And now I'm going to give you a moment, try to finish the rest of the table yourself. I'm not going to be showing you all the answers, but I will show you the last row because if you have been doing it correctly up until the last row, you should get the same value. So for the last month in December, you should have got that the balance at the beginning of the month is $493.44. And if we earn 0.5% interest on that, that will be 2.47, which means at the end of the year, we have accumulated $495.91. And now I want you to think, how much interest was earned throughout the year? What do you think? Use the table, use what you know to make a conclusion. So throughout the year, we have made all of these deposits, which means we have deposited $40 12 times, which means that we have invested $480. So of that $495.91, $480 of it was our own money that we invested. So then the interest would be the final amount we have at the end of the year minus what we invested, which will be $15.91. And so that's how much interest that was earned throughout the year. And you can also one other option, which is a bit more tedious, but if you're unsure or you just want to double check for your own learning, if you add up this column, or especially if you are working with Excel or like any online spreadsheets to fill out these tables or create one for yourself, that one is actually a simpler tool to get the sum of sum of this column. You should be able to see that the sum of this column will also produce $15.91. Now let's go on to our next example. So now here we have our ordinary annuity because we are depositing at the end of each year. So we are depositing $1,000 at the end of each year into an account that earns 6% per annum and it's compounded annually. And we're asked what will the total in the account be 5 years after the first deposit. So again, another exception here, just because I want to show you a lot of variety of problems. In this example here, we are told that when the account is opened in year 0, the account has $1,000 in it already. So this would be different from regular ordinary annuity problems you might see, because in those problems, it is assumed that you start with $0. So in the first year, because you haven't added any money in, you actually don't earn any interest. So then when you deposit money at the end of the first year is when you start earning interest. But in this case, we already have $1,000 in the account, which means that after year 1, we are earning interest on that $1,000. And it's more just that every year following that, we're earning more interest because we're depositing more and more money. So after 1 year, the account, and because it's 6% per annum and it's compounded annually, we can conclude that I here is 0.06, and we don't have to do any divisions here because it's compounded annually. So 1,000 times 0.06 is $60 interest. So at the end of year 1, we have $1,000.60. And remember, you can also, if you just multiply by the interest rate, you're going to get the interest value. But if you multiply by 1, this is the number 1, plus I, then you're going to get the total value because we are also accounting for the $1,000 that we had and the interest that we earned from that, so $1,000 and $1,060. So after that interest is earned, then another $1,000 is invested. So now we have $2,060. Or in other words, 1,000 plus 1,000 times 1.06, which is directly from here. Now, this is where it's going to be different from compound interest that we saw, in the sense that here we are earning interest on this value and we're earning interest on this value. But so we have two values that are earning interest for us, whereas compound interest was this value and it just keeps compounding on this. So then we just raised it to the power. But now we have an addition. So when we have the interest earned the second year, we have two terms that we have to account for. So after 2 years or after another year has passed, the account earns 6% on the $2,060, which means the total, and again, remember, this term here is the $20.60. So all I've done is rewrite this here and then earn that 6% interest on there. But again, because I want to know the total, that's why I have 1 plus I here, 1 plus I here, which means that if I distribute this value per term, using distributive property, then I have earned 6% interest on the $1,000. But then from the first year, I already had $1,060, and then I earned another 6% interest on that. So the original $1,000 was compounded 2 times at the rate of 6%, whereas the second $1,000 deposit only earned interest once, which is why we have just 1.06 here, and here we have to the power of 2. So now, following this pattern, can you produce a similar expression for the interest? And this is just for the interest after 3 years. So that interest here. So keep in mind From the first year, we have 0.06, but after another year, this is now has earned interest 3 times. This is the original $1,000 we invested. Now we invested another $1,000, which already earned um, a 6% interest, and now because another year has passed, this is earning another interest, so it's to the power 2. And finally, we invest another $1,000, which this has only been in the account for 1 year, so it only earns an interest of 6% once. Now, I can also ask you, what would the total be after 3 years? So this is the total, this is just the interest. And in this case, the only difference would be instead of 6%, we have 1 plus the 6%, so 1.06. And this will give you the total value after 3 years. Now, after 5 years, the original $1,000, oh, sorry, an error here. These should all be 6 because it was 6%. So the original $1,000 that was in the account before we earned any interest, after 5 years of earning interest, it has a value of 1.06 to the power of 5. Again, 5 years have passed. The next $1,000 we invested has only earned interest over 4 years, which is why it has a power of 4. And the pattern continues on until year 5, where at the end of the year, you invest $1,000, but that $1,000 hasn't earned any interest yet. So it just remains as $1,000. Whereas all the other ones have earned interest for at least 1 year. So after 5 years, the total in the account will be $6,975.32. And this value is actually correct with the 1.06. So that's how much interest you will earn if you invest $1,000 at the end of every month and you're earning 6% interest compounded annually. And now we're asked to show that after 5 years, we have earned $975.32 in interest. Well, you started with $1,000, which you invested, and then you invested $5,000 over the next 5 years, which again, similar to the question above, our investment was $6,000. This also accounts, again, for that $1,000 that we had at the beginning of the year 0. Whereas in ordinary annuity, this might have just been 5,000, and then you wouldn't have earned interest the first year. And consequently, all of these, their powers would be subtracted by 1, because the first year, again, you have no money in the account, so you don't earn interest. So actually, you would only have five terms, but here it was different because we already started with $1,000 in the account. So if we invested $6,000 and our total was $6,975.32, then our interest would be that total value at the end, take away our investment, which is precisely $975.32 in interest. Now, if we were to use the formula from above, so far in the first 2 examples, I wanted to show you per period how the annuity is changing and how the values are changing depending on how much you're depositing. But we had these 2 formulas at the beginning that we saw, and these actually work. So all I've done is just copy these here for you. And I'm showing you here now that if we use this formula, we get the same value. Again, keep in mind in this question, because we had $1,000 at the beginning, we are actually considering 6 periods here because you are earning interest the first year, whereas in ordinary annuity, you might not be earning that. This would actually be more of a better example, perhaps, for annuity due, where you are investing at the beginning of it every year, which then would account for the fact that we have um, 6 periods in over 5 years. And really, the only difference between ordinary annuity and annuity due is the number of periods and the number of payments that are made. Because if you, again, just think of the first year, if you invest at the beginning of the year and you earn interest over that year, then you've earned interest over that or the period, not it doesn't necessarily have to be per year, but if we're thinking compounding annually, then you are earning interest at the end of the year. Whereas if you only invest at the end of the year, then that first year will go by and you haven't invested anything, so you didn't earn interest, and it's only 5 periods in that case. So that's just a little bit of explanation for you of why we are counting n is equal to 6 here. So my regular payments per year were $1,000. And here we had 1 plus 0.06, which is 1 point, or sorry, 0.06 was my interest rate, and raising to the power of 6 for 6 periods, minus 1, which is the minus 1 here, and divide by that interest value again, 0.06, gives me $6,975 dollars and 32 cents as required as we saw above. And again, here we have 6 payments over 6 periods. Now, for the next one, next problems, we're really only going to be using the formula, so I won't show you this step by step for the periods anymore. But if you are unsure of any of them or you just want more practice, then you can definitely build that table for yourself for any of the problems and see that how the value of your deposits are changing per period. So question number 3, Flora deposits $1,500 every 3 months for 2 years into a savings account that earns 10% per annum and it's compounded quarterly. How much money will she have accumulated at the end of 2 years? So here we want to know the future value, which means we are using this formula. So we have to start by figuring out what each of the variables are, and specifically R, I, and N. So R, which are the regular payments per period, are going to be $1,500 or $1,500. And these payments are made every 3 months, which coincides with our compounding quarterly, which means that we are making 8 deposits over 2 years because we're depositing every 3 months. And so every year we have 4 payments and it's 2 years. Now, for the interest rate, it was 10% per annum and it is compounded quarterly. So I is going to be 0.1, which is just the 10%. This is 10%. And divided by 4 because it's quarterly, which gives us 0.025 or 2.5%. Now, substituting all those values into our formula, we find that future value is equal to 1,500. Here we have 1 plus, this is now our I, 0.025 to the power of 8 because it was 8 deposits or compounded 8 times. And then the rest we just get from the formula minus 1 here, and then divide by I again, and we find that we have $13,104.17. So at the end of 2 years, Flora will have accumulated $13,104.17. And again, I could ask you here how much was earned in interest as compared to how much was deposited. So you would just have to find 8 times 1,500. So $12,000, so $1,104.17 were earned in interest. Now, our next question, this is again also a future value here. Ali wants to retire in 25 years with $1 million in savings. His current investments are earning 12% compounded annually. What regular annual deposit must he make to have the required amount at retirement? So this is actually an amazing example of why annuities are important because you might be saving up for a specific value. For example, you can set this up really easily in your bank account where you a certain amount is deducted automatically at the end of each month so that you are planning to invest for a future goal, whether that be retirement, a vacation, or even to pay for college or university. So uh, it helps us figure out how much money we need to be investing each period. So in this case, the future value that Ali wants is $1 million. And it he wants to save over 25 years. So N here is 25 because it's annually. And so because again it's compounded annually, the interest rate is going to be the same as our per annum rate. So 12% is 0.12. So now substituting into the formula from above, we have $1 million is going to be equal to R times 1.12 to the power of 25 minus 1. And now keep in mind here, when you're dividing, this is just I. Don't confuse these two. Don't put 1.12 here again. It's just 0.12. And now we want to solve for R, which is our regular payments. And this is just a bit of algebraic manipulation. We multiply by 0.12, and then we divide by this numerator here, and we get $7,499.97. Or if we just round up, because you can just, when you're investing, you can if you invest a little bit more, then you earn a little bit more. You want a minimum of $1 million, but if you have a little bit more, that's totally okay. So either of these two answers would be acceptable here. So we can say he needs to invest approximately $7,500 annually so that he has $1 million in his retirement after 25 years. And now here, if he's investing this much annually, how much of the $1 million is interest that was earned? So if he's investing $7,500 annually for 25 years, this is just multiplication, we get that has invested $187,500, which means that if we subtract that from the $1 million, he has earned $812,500. So of that $1 million, almost 80% of it was interest earned, which is a pretty good deal. And you actually won't see this rate in banks often, as you can clearly see why, but in this problem, that's how much interest he would have earned. Now, this is a problem where now we're working for present value. And it's also another application of annuities. Here we're paying for college or university. So Zane saves in an account that pays 9% compounded annually. He plans to go to university next year. While he's at university, the annuity provides him with annual payments of $5,000 for tuition for 4 years. How much money must be in his account now if the first payment starts in a year? So he wants to put a certain amount of money into a bank account right now. This amount will be earning interest over 5 years because he doesn't go to university until next year. However, whatever money is in that account right now earns that interest in 1 year, but then he's now depositing, or sorry, he's withdrawing $5,000 after 1 year. So now we actually have the example of withdrawal. And so then the next year when he's earning interest, there's $5,000 less in his account, which means that the second time he earns interest, he's earning less interest because there's less money in the account. But he doesn't necessarily, if he wants $5,000, he doesn't necessarily need to put $20,000 in the account right now because he's also counting that, okay, I'm earning interest, so perhaps I can put less money, and then by the interest that I earn, I can earn up to that $20,000 that will pay for my tuition over 4 years, which is exactly what we want to solve for. So how much money needs to be in the account right now for the first payment to start in a year, and he has consequent $5,000 payments every year. So here we're solving for the present value. From above, we have this formula. So here, the R here, which is the regular withdrawals, are $5,000. And our I interest rate is 9,000, or sorry, 9% or 0.09, and it's compounded annually over 4 years. So N is equal to 4. And the reason it's 4 here and not 5, because in the last year, once he takes that last $5,000 out, then there's no money in the account. So he just wants it over those 4 years. He's taking the money out at the beginning of each academic year. So assuming he's in university over the 4 years, he takes money out at the beginning of year one, at the beginning of year two, at the beginning of year three, at the beginning of year four. So that's 4. So the present value is going to be 5,000 and times 1 minus 1 plus 0.09, which is our interest, to the power of now -4. And think now because we're working backwards, right? We're working backwards in time, so it's a negative here. And then divided by 0.09. And exactly as I mentioned, he does not need to invest $20,000 right now. He only needs to invest $16,198.60. So that over 4 years, he can earn $5,000. So breaking this down so it's a little bit visually more understandable. So the first $5,000 will only earn interest once because after 1 year, he withdraws that $5,000. The second $5,000 has been in the account twice. So or the $5,000 is the future value in this case, right? But the present value of that second $5,000 is that it has earned interest by 9% twice, which means that the present value right now of this can be calculated as the present value times 1.09 to the power 2, which is why here we're dividing it. Same for the third year, and finally the fourth year. The $5,000 has been in the account over 4 years and has earned interest 4 times. So then, just to break it down here as well, the value of the payment of the first year will be, this is just again for the first year, the present value is $4,587.16. And that's how much amount needs to be deposited so that after 1 year, he has $5,000. For the second year, he needs even less because he's earning double or he's earning interest twice. So then for the second year, it's $4,208.40. And for the fourth year, it's even less than that. It's $3,542.13. So that over 4 years of interest, that will become $5,000. And so that's an example of how annuities work when it's withdrawal instead of depositing. And now let's look at our last example. We're also now solving for present value here. So Nilu bought a jet ski for $1,500. She arranged to make payments to the store at the end of every month for a year. The store charges 11% per annum, and the interest is compounded monthly. So first, how much is each monthly payment? So the present value that must be paid is $1,500. So actually, correction, we're not solving for the present value, we're solving for the regular payments, in this case, monthly payments. The annual rate here is 11%, but because it's monthly, we divide by 12, which gives us 0.00917. Or again, as I mentioned, I highly recommend you use the 11 over 12 in your equation as I did here. And because it's over 1 year, the number of periods n is going to be equal to 12. And so substituting into the formula, we for present value, we have the following equation, but now we're solving for R here for the regular payments. So with some rearranging, we find that R is $132.57, which means that she must make monthly payments of $132.57. And so how much interest is Nilu paying? Well, if she's paying this much over 12 months, then she has paid $1,590.84. And remembering that the jet ski itself was $1,500, then she pays $90.84 in interest, which is not a bad deal if you don't currently have that $1,500 right now, but you want to make a purchase, then you might make use of this. Consider programs such as Afterpay that offer these interest rates to make monthly payments for big purchases. And that was the end of our lesson for annuities. I hope you learned lots, and check Google Classroom for any additional tasks. Don't hesitate to reach out if you have any questions, and I will see you all in our next class.